Hello students, welcome to series of lectures on linear integrated circuits and application. In this video, I am going to explain about the active wideband pass filter. So in the previous video, we have already seen high pass filter, its response, and also low pass filter, its response. So let us focus our discussion on wide band pass filter. Let's get started. So these are the two important lecture learning outcomes of today's video. You will be able to understand the op-amp based active filters, and you'll be able to analyze the operation of wide band pass filter. So this is the pin diagram of IC741. Please go through this, each and every pin of this. Alright, so what is an active filter? So an active filter is a type of filter which includes one or more active circuit components such as transistor or op-amp. So normally we are going to be designing any kind of filter using active component called operational amplifier. So what is the active band pass filter? So a band pass filter passes signals only a certain band of frequencies and while rejecting all signals outside of the band. Okay. So you can also see from the picture in this slide. So this is the frequency response of the band pass filter. Okay. So how it is looking like? So this is the band of response we are interested in. Okay. So the frequencies which are allowed into this band we are only considering. Okay. And outside of the band, this we are not going to be considering. So this is the reason I'm calling this is the stop band, the outside of the band of the frequencies, whatever that is coming. So these are the stop band. So here also this is stop band. Okay. So only the pass band is nothing but the band of frequencies we are interested in. So this is the frequency response of a band pass filter. Alright. So what are the categories of the band pass filter? So mainly we can see that two important categories for the band pass filter. The first one is a wide band pass filter and then narrow band pass filter. But on what basis we are going to be dividing these two important considerations? Okay, with respect to the quality factor. Okay, the quality factor or the figure of merit, both are same. So on the basis of quality factor, we are going to be dividing the band pass filter could be a narrow band pass filter or the band pass filter could be a wide band pass filter. So if Q is less than 10, so which is nothing but wide band pass filter. Okay, and if Q is greater than 10, then this is the narrow band pass filter. Okay, so as the Q is less than 10, we are calling the band pass filter is a wide band pass filter, and Q is greater than 10, then we are calling the band pass filter is a narrow band pass filter. Okay, so on the basis of the quality factor only, we are going to be categorizing the two important conditions for band pass filter. Okay, so the higher the value of Q, this is very important point I have mentioned in the slide. The higher the value of Q, the more selective is the filter. Okay, or the narrower is the bandwidth. So that is what actually we are going to be desiring the component. So as we already seen the frequency response. So this is the frequency response. There are total so many categories we are going to be accompanying. The total how many number of frequencies that you want to allow, and what is the bandwidth that is requirement for designing of any kind of application. Okay, so for an application, I required only the bandwidth is very less at that point of time. So I am going to be seeing the band pass filter should be this one. Okay. So when comparing with the response of the frequency response of here, the 1 and the 2 figures, so here the bandwidth will be more. Okay. But here the bandwidth will be less. Okay. So that should be depends upon the situation of an application. Okay. So mainly the relationship between the Q and the bandwidth which is given by the quality factor Q is equals to resonant frequency by bandwidth or central frequency by bandwidth. So this I am calling as a central frequency or the resonant frequency, both are same. Okay. So if you want to design the bandwidth is very less, that means the quality factor will be high. If the quality factor will be high, that is more than 10, then we are calling that as a narrow band pass filter. So the narrow bandwidth you are going to be getting, so that quality factor will be high. And similarly, if you want to design the bandwidth will be more, then obviously quality factor will be less. So that means what is the filter that you are designing? Narrow band or wide band? So in this case, you are going to be designing wide band pass filter. So that is the reason. Alright, so this is the circuit diagram of the wide band pass filter. So the wide band pass filter is very simple for us, because we have already understood what is the circuit diagram of the high pass filter, and we also know what is the low pass filter. When it comes to the first order, if I ask you to design the first order wideband pass filter, we are going to be taking into consideration of first order active high pass filter and then first order low pass filter. Okay, so these two circuits, they are cascading, that's all. It becomes the first order wideband pass filter. So see the circuit here. So this is the first order active high pass filter. Okay, and whose output of this first order active high pass filter will be given to the input to the first order low pass filter. So this overall will becomes first order wide band pass filter. That's all. It's very pretty simple for us to design the wide band pass filter. Okay, so wide band pass filter, nothing but the quality factor should be less than 10. So this is the way how we are going to be designing. And you can also we also know the what is the transfer function for high pass filter separately and what is the transfer function for low pass filter separately. So in order to get the transfer function for first order wide band pass filter, we are going to be multiplying. Okay, the two transfer function we are going to be multiplying. That's all. So it becomes, sorry, first one is a high pass and the second one is a low pass. So it becomes the first order wide band pass filter, and you can also see the frequency response of the wide band pass filter. So wide band pass filter, nothing but we are going to be expecting the bandwidth will be more. The bandwidth will be more. So if it is first order, so during the initial stage, the plus 20 dB per decay, that is the slope, and the minus 20 dB per decay, that is the roll-off rate at the other end. Okay. But if we take the second order active high pass and second order active low pass, that means we are designing the second order active wide band pass filter. So at that point of time, so this should be 40 dB per decay. The slope could be 40 if the second order you are designing. Okay, and this is minus 40 at the other end. So that is only the point you need to do. Alright. The same thing I have mentioned. This is the overall transfer function of the first order active wide band pass filter. Please remember. And this A01 is a pass band gain for high pass, and this is A02 is the pass band gain for low pass. Alright, next the category is that narrow band pass filter. So on the basis of the quality factor, we are going to be dividing whether it is narrow or wide band pass filter. So narrow band pass filter, normally we are concentrating on the infinite gain multiple feedback, that is IGMF configuration. Okay, so what is the configuration that we are going to be taken into consideration for narrow band pass filter is that infinite gain multiple feedback. Okay, you will be getting the gain should be very high practically, and the multiple feedback you are going to be taking into consideration. Okay, so this is a circuit diagram. This is a circuit diagram where you are witnessing how many number of feedbacks which are there. Two feedbacks, feedback 1 and feedback 2. That means a multiple feedback infinite gain that you are going to be designing. Okay, so this is the frequency response. Obviously the bandwidth will be very less when in comparison with the previous category of the band pass filter. Okay, and to do the analysis, I am going to be considering admittances here, because that is very simple for us to do the analysis part. Okay, so if you consider admittances and if you apply KCL and Ohm's law or nodal analysis, whatever that is comfortable to you, and you will be getting the transfer function with respect to the narrow band pass filter. Okay, so this is the circuit diagram for the narrow band pass filter. We have modified in such a way that we are considering admittances y1, y2, y3, y4 and then y5. Okay, and the two nodes also we have mentioned. So at node A, what is the direction of the currents? Okay, accordingly how many number of currents which are entering and how many number of currents which are leaving from that node. And if you apply KCL, and you will be getting one equation. And similarly, if you apply KCL at node B, how many number of currents which are coming and how many number of currents which are leaving from that node. And obviously when you compare the two equations, you will be getting voltage transfer function. So that is what. So this is the analysis. So please go through this. This analysis is very simple if you understand what is KCL and what is Ohm's law. Okay, so accordingly we have derived it. So this is the total voltage transfer function we'll be getting. Okay, and we are going to be assuming that y1 equal to conductance G1, y2 equal to capacitor, y3 is capacitor, y4 is the conductance, y5 is also conductance. Okay, so for the above filter to be band pass filter, so this is the way how we are going to be getting the voltage transfer function in terms of conductances and then capacitors. So the total overall transfer function we will be getting for the narrow bandpass filter should be this. And this transfer function is very similar to the transfer function of the resonant RLC circuit. Okay, you can also design the RLC circuit and you are comparing this. Okay, when you compare the resonant RLC circuit with the transfer function that you have got after doing the analysis of this. Okay, and when you compare, you will be getting V naught of S by V of S equal to minus G dash by G plus SC plus 1 by SL. Okay, so what is G dash and everything that we have mentioned in the next slide. So this is the slide where you are going to be comparing the resonant RLC with the transfer function whatever you have already got. Okay, so G dash is the G1, G is what, L is what, C is what, everything that we have compared. And what is the resonant frequency, that is omega naught under root equal to 1 upon under root LC. Okay, if this is F naught, so this becomes 2 pi will becomes in the denominator on the right hand side. Okay, so the gain at resonance and every parameter that we are going to be evaluating. Okay, what is the quality factor? That is omega naught L by R, which is equals to omega naught into RC. Okay, so everything that we can easily find out if we compare the transfer function of the analysis with the resonant RLC. Okay, so every parameter that is very well known to us. Okay, so what is the standard form? The standard form of the bandpass filter, which is given by H of S equal to minus A naught alpha omega naught S by S square plus alpha omega naught S plus omega naught square. Okay, so here what is alpha? Alpha also we have given in terms of the quality factor. So as the quality factor increases, we can achieve the ideal bandpass filter response. So that you need to remember. This is a very important point from the theory. Okay, this is the conclusion. As the quality factor is increases, we can achieve the ideal bandpass filter, the flat response that we are going to be getting if the quality factor is increases. Thank you, students. Thank you for watching this video.